Hello everyone, welcome back. In this video we are going to apply the techniques we have learned in the previous videos for plotting schematic rough sketches of polynomial and rational functions to solve some inequalities involving polynomials and rational functions. So we're going to just do some toy examples that are just for the sake of exercise, and it'll just be a couple examples in a short video. So for our first example, let's consider this polynomial here, and we want to solve for all x such that that polynomial is greater than or equal to 0. So it's already in factored form, which is great because that's what we need to be able to graph it roughly quickly. So what's the first step? Well, once it's factorized, let's write out the zeros, which are 1, 3, and 4. And their multiplicities are 2, 1, and 3 respectively by looking at the exponents. And as we explored in the previous video, one of the important things for understanding, for piecing together a graph is to look at the zoomed out form. So that is for very large x, what is this polynomial approximately equal to? And for very large x, the 1, 3, and 4 are insignificant, so we can simplify, or we can approximate each of these factors by simply x, and that gives us minus 2 times x squared times x cubed, which is minus 2x to the 6. X to the 6 is sort of like a parabola, and minus 2 makes it a flipped upside down sort of parabola. So now we know when x is very large, this is what the graph will look like, roughly. So now we have enough information to give a rough sketch, and let's go through and do this again ourselves. Let's do this from scratch. And here is how we'll go through this process. So we know that 1, 3, and 4 have some zeros. Those are the interesting places. So 1, 2, 3, 4. At 1, 3, and 4 we have zeros. And we know the zoomed out behavior. So once we get far enough away from these zeros, we know it's going to be going downwards. And furthermore, let's see, when we go up to 1, and it's multiplicity 2, so that means it looks like a parabola, but it's going to be an upside down parabola to meet the continuity condition for polynomial functions. Then the next one is a multiplicity 1 root at 3, so that means that we go through it like a line. And then at 4, it's multiplicity 3, so it's going to look like a cubic, but it's going to have to go downwards. And then that will let us meet up with the arrow over here. So that is a graph, a rough sketch of y equals minus 2, x minus 1 squared, x minus 3, x minus 4 cubed. So with this graph in hand, we can now solve for when is this function greater than or equal to 0. In particular, that means when is this graph at or above the x-axis? So one thing is for sure, when it hits 1, it comes up, hits 1, and then goes down immediately. That is a place where the function is greater than or equal to 0. And then once it goes from 3 to 4, we could see that's the other spot where it's greater than or equal to 0. So that's one way of writing the solution set. In Math 3, we're interested in writing it in set notation. So we can also say that the solution set is the set containing just 1, that one singleton point right there, along with, via a union, the closed interval from 3 to 4. And so we can say that x, or the solution, any solution x is an element of this set of points. And let's write this as a number line. So it's 1, and then also from 3 to 4, and we make the line bold in between to indicate that those are all included. So that's one way of writing a solution set graphically. Let's vary this problem. It's the exact same polynomial, but now we want when is it strictly greater than 0. So we don't want to include when the function is on the x-axis. So in that case, x equals 1 is no longer a solution, and neither are the endpoints. So what we can say is that the solution set is all x in the open interval from 3 to 4. And we can write this solution set as from 3 to 4, circles to be an open interval, and then we can fill it in with a bold line. And so open interval from 3 to 4. One more variation on this problem. What about when it's strictly less than 0? So when is the graph of this function strictly below the x-axis? So if we look at this, it comes for negative x, it's definitely below the x-axis. And then we get up to 1, but not including 1. That's all below the x-axis. And then once we start going above 1 again, it's below the x-axis up to 3. And then after 4, it's below the x-axis again. So we can say it's all the x in the open interval from minus infinity to 1. And then that lets us exclude 1. And then we start up with an open interval again from 1 to 3. And then we skip everything from 3 to 4. And then we go from 4 onwards. And again, using a number line, we can go up to 1, open, and then everything back there is part of it. And then we go up to 3, and that is all part of it, but we don't include 1. And then we skip everything from 3 to 4, and then from 4, not including 4, but after 4 onwards, that's part of the solution set again. Okay, so that was a polynomial inequality. And to finish off, let's look at a rational function inequality. So in this case, we want to know when is this rational function greater than or equal to 0. So we use the techniques from the previous video of creating a rough sketch of this rational function. And to do that, we find the zeros and the poles. So the zeros are the roots of the numerator, 1 and 3, and they each have multiplicity 1. And the poles are the roots of the denominator. Then the root is 2, and that also has multiplicity 1. Zoomed out version, we simplify we approximate everything by saying that x minus 1 and x minus 3 are both x, and x minus 2 is x. And that gives us that x is what this should look like when we are zoomed out, which means that it should look like, a line when we're zoomed out. And then that gives us a picture, which we will reproduce right now. Let's delete that. And so what we have are zeros at 1 and 3 and a pole at 2. So vertical axis, 1, 2, 3, zeros at 1 and 3, pole at 2. We know that for large enough values, it's going to go off in the positive direction, and for negative enough values, it's going to go off in the negative direction, just like y equals x. And then it's going to, on the left-hand side, come up to the 0. It's multiplicity 1, so we go straight through it. We go up to the asymptote. It's a multiplicity 1 asymptote, so it's positive on one side, which means it's negative on the other. Then we come up to the 0, multiplicity 1, 0 at 3, go right through, and then we connect up. And that's our picture. So when is this greater than or equal to 0? That's when the graph is at or above the x-axis, and we can see that when x is less than 1, it's below the x-axis. When x is 2, the function's simply not defined, so we have to be sure to exclude it from the solution set. And when x is from 2 to 3 exclusive, it's below, and then from 3 onwards, it's above. So from -1 to 2, that is when it is at or above, where we include 1, and that should be a positive 1. And so we include 1 and exclude 2, and then we include 3. So on a number line, what would this look like? It would look like from 1 inclusive to 2 exclusive. We want to include this interval, so bold that in. And then from 3 inclusive onwards, we can go all the way to infinity. So anyway, that is the solution set for this rational function. So what we're not covering in this video is inequalities between two different rational functions or two different polynomials, or mixes of rational functions and polynomials. And the thing is, all you have to do is move everything to one side so that you've got a 0 on one side, and also every polynomial is a rational function already with 1 as the denominator, so it's all the same method. So anyway, we could have also done applications and all that, but the point of this video is just to see how to do the mechanics of solving some inequalities of these sorts of functions. So I'll see you all next time. Goodbye.